Hello, Dr. Frowney. This is Tristan. For my part, discussing multi-rate filter design, I will be talking about signal rate conversion, and more specifically, I'll be talking about decimation, because I did not find that Purcell's paper gave a very good explanation of what decimation was or why it was useful. Decimation is the equivalent of sampling an analog signal, but as it relates to digital signals. Where sampling converts an analog signal, which has a continuous time, to a discrete time signal by taking out points at every x time interval. Decimation reduces the sample rate of a discrete time signal further by discarding the extraneous values from a discrete signal. Generally, only every mth signal is kept, where m is called the decimation factor, leaving a signal that is only 1 mth as long and has 1 mth the sample rate. Decimation is a two-step process. First, the signal that needs to be decimated has to be low-pass filtered to prevent aliasing, so the signal can later be recovered. An FIR filter needs to be used, not an IIR filter, because if an IIR filter is used, you will need to calculate from the filter, you'll need to calculate every single point in the initial signal. Whereas if an FIR filter is used, you will only need to calculate the output for every mth piece of the signal. And the low-pass filter used needs to have a sufficiently high cutoff that it will not cause aliasing in the new signal. So its cutoff is usually equal to the original signal's Nyquist rate divided by half of the decimation factor, m. After that, the unwanted data points, all but every mth, are just deleted from the signal, which leaves you with the decimation of that signal. Next question was, why is decimation actually useful to us? Firstly, decimation can be necessary as a step to converting between systems. Decimation can only be done to make integer conversions of a signal, but in combination with interpolation, it can be used to make any fractional adjustment. And this can be necessary to convert a signal to, say, the 44.1 kilohertz range, so if audio needs to be transmitted at that range. But more importantly, decimation is useful because it drastically reduces the number of operations that a chip must take in order to process that signal. Since most filter operations take a time that is directly proportional to both the sample rate of the signal and the length of the signal, a decimation by m gives an improvement in the number of operations that is quadratic, an m squared reduction. Decimation, however, does not reduce the initial cycles to accumulate the data, so it is only worth using for computational savings if the computation time is significant relative to the collection time where you're accumulating data. This limitation can be partially overcome by decimation in sequence, multiple stages of decimation. For instance, rather than doing a decimation by 4, doing a decimation by 2 followed by another decimation by 2 would allow the second decimation to begin while the first decimation was still in progress, and it could give you significant time savings. Finally, the only reason that we're able to use decimation for these purposes is that the decimated signals can be reconstructed without loss across a specific range. This is why the selection of the cutoff frequency for the low-pass filter is, of course, essential. In order to reverse decimation, you must use interpolation, which is actually surprisingly simple. You replace all the lost data points that were deleted with zeros, and then filter again. That's about all I had for this. I really wish I had a whiteboard to work with and could do the little question and answer period, but that's not practical since this is being done remotely. So, thank you for your patience, Dr. Froney, and have a good Christmas.